We now need to show that the factorization that we had previously here is unique. That is unique in the only way it can be unique, which is unique up to order. So remember, our primes are distinct in this factorization, and the r's are natural numbers. So the bigger than or equal to 1 are the number of times that prime shows up. So how can we prove that the factorization is unique? Well, we're going to suppose we have two factorizations and show that up to reordering, they're actually the same thing. So suppose there exists distinct primes P1 through Pm and Q1 through Qj. There doesn't need to be the same number of primes necessarily in this factorization. And exponents R1 through Rm and S1 through Sj, such that we have this happening. So the P's are distinct, the Pi's are distinct from each other, the Qi's are distinct from each other, and they both assemble to get n in this way. What we want to show to prove that these are actually the same is to show the same number of primes show up. So m equals j. So there's m primes p, and there's m primes pi, and there's j primes qi. So m should be equal to j. And we should be able to, oh, I misspelled reordering. Oops. We should be able to reorder them so that the pi and qi are exactly the same. So up to reordering one of the sides, our factorization matches up completely, and our exponents are also equal. So this is what uniqueness means. Up to reordering, they're actually just the same primes that show up and the same exponents as well. Okay, so suppose we have all of this. Let's start to prove that this is true. We know that by stripping off a P1 and letting the rest of the part here, so we're going to strip off one of our P1s, and the rest of it we're going to call K. So P1 times K is a product of primes Q1 to the S1 all the way up to Qj to the Sj. So by the theorem that or the helpful lemma that we proved a couple videos back, whenever P1 divides a product of primes, P1 has to be equal to one of the primes in the list. Now, we're allowed to reorder, so I want to interchange the roles of Qi and Q1 just to make the order, the indices align. So we're going to swap the role of Qi and Q1, and that will tell us that P1 is Q1. Okay, so I know that in this list, I've reordered it so that P1 and Q1 are the same. Now we need to check if the exponents are the same. Well, one of two things is going to happen. The exponent on P1 is either bigger than or equal to the exponent on S1, that's R1 bigger than or equal to S1, or the opposite's going to happen, R1's less than or equal to S1. Let's suppose for a moment that R1 is bigger than or equal to S1. Then we have a Q1 to the, we have a Q1 to the S1 on this, sorry, a P1, because P1 and Q1 are the same. We have a P1 to the S1 on this side, and a P1 to a bigger, possibly bigger exponent than S1 on the other side. So we're going to divide them out. And I'm noticing a typo here. They should say S2 here. But when we divide out all those S1s, we get a P1 to the R1 minus S1. If R1 minus S1 is positive, that is, this exponent still appears, then P1 is still going to divide the right-hand side. But it's not possible for P1 to still divide the right-hand side because P1 was Q1, and the list of primes was distinct. So all these primes, Q2 through Qj, are different from Q1. And P1 was Q1, so P1 is not equal to any of these. So it must be that R1 is equal to S1. If R1 is less than or equal to S1, the other case, it's the same argument. You just divide the powers over to the other side. So the outcome of this first step is P1 is equal to Q1, R1 is equal to S1, and we cancel them on both sides. If we cancel them on both sides, we have a factorization with less elements. And we keep going. We keep canceling the p's on the left. And eventually what we have to get is 1 equals 1, and our primes will match up exactly. So there's some details that need to be filled in at the end there, but that's roughly the idea.